Hi, I'm Ming, a master student from Tianjin University. I'm excited to present our recent work on their library testing. This work was done by Tianjin University, and we are very honored to receive the FSE 2020 Distinguished Paper Award. Nowadays, deep learning applications have been widely used in safety-critical tasks such as autonomous driving, medical diagnosis, and aircraft collision avoidance detection, of which the safety and quality are very important. The development process of deep learning applications can be seen as developers leverage deep learning libraries to program and construct deep neural networks. The model is obtained by training the dataset. Each stage in the process could finally affect the quality of deep learning applications. That means the bugs may occur at application level, library level, or even infrastructure level. Many works focus on the bugs in deep learning models and the deep learning source program. The deep learning library is the foundation of deep learning application, and its quality determines the safety of deep learning application. Therefore, it's very important to detect bugs in the DL library. In this paper, we focus on the bugs in the deep learning library. However, it's difficult to detect bugs in DL libraries. There are two main challenges in this task. The first is how to obtain a large number of test models. Relying on existing models to test the DL libraries may face a problem. Existing models usually focus on popular tasks, and these models can only invoke a limited portion of library code. At the same time, it may cost a lot of time to collect a large number of models. The second challenge is how to expose bugs triggered by the model. Uncertain factors such as randomness may cause inconsistencies in outputs between different DL libraries. Inconsistent degrees from real bugs may be similar to or even smaller than those from uncertain impacts. A recent work on ESEC 2019 proposed the Cradle, which is a state-of-the-art approach to detect bugs in deep learning libraries. Cradle leverages real-world models and inputs, using carriers as the front end of different backends, such as TensorFlow, Theano, CNTK. The model will get different outputs with different backends. Cradle uses differential testing as test oracle, defines metrics to measure the inconsistencies between different backends to decide whether there are bugs in the deep learning library. The main contribution of Cradle is to solve the test oracle issue of their library testing, but it may also face the two challenges. Based on those, we propose Lemon, a deep learning library testing approach via model generation. To solve the first challenge, we define 12 mutation rules to mutate existing real-world models to obtain a large number of models. To solve the second challenge, we use heuristic-based methods to generate models which amplify the inconsistent degree between different libraries to distinguish between inconsistencies caused by real bugs and the inconsistencies caused by uncertain factors. Now, let's quickly look through the workflow of Lemon. Lemon designed 12 mutation rules to generate models. By applying mutation on existing models, we can obtain a large number of mutated models and easily obtain the outputs of models on different libraries. Lemon also uses differential testing as test oracle and uses the same metric as Cradle to measure the IC between different libraries. We use a red box to highlight the main contributions of Lemon to solve the two challenges. Lemon designed two types of mutation rules to generate a mutated model based on existing models to solve the first challenge. For the second challenge, we use heuristic-based strategy to select mutation rules and seeds to generate models that can amplify the degrees of IC between different libraries instead of using random strategy. More details would be explained later. So, firstly, let's see the intact layer mutation rules. Lemon defines 7 intact layer mutation rules. Intact layer mutation involves mutation on the entire layer and thus tends to introduce relatively large changes to a model. For example, Lemon can add, copy, and delete a layer in the model, or switch two layers in the model. Besides, Lemon can add a series of layer combinations to the model, replace or remove the activation function of a certain layer. In-the-layer mutation is operated on the neurons of a layer, which is more fine-grained than intact layer mutation. Lemon defined 5 in-the-layer mutation rules, including adding noise to neuron weights, shuffling the connection weights of a neuron with the previous layers, and eliminating the effects of a neuron on the next layers. Besides, Lemon can invert the activation state of a neuron by changing the sign of output value, or switches two neurons in a layer to exchange their effects on the next layers. The other important part in model generation is the heuristic-based selection strategy, which determines the seed model and the mutation rule used in each iteration. Let's see the seed model selection at first. In general, Lemon prefers to choose seeds which are rarely selected in history in order to increase the diversity of the generated models. Lemon uses the initial model as seed model. In subsequent iterations, Lemon heuristically selects the seed model. Once the mutation rule is determined, the mutated model will be generated. In each iteration, the mutation rule performs the first-order mutation on the seed model, and the mutant would be put into seed pool. High-order mutation is achieved by accumulating the first-order mutation in each iteration. Lemon records the number of times each seed model is used and calculates the score and the probability of being selected. For each seed, a seed with a larger score has a higher probability of being selected. Then, we use the roulette selection strategy to choose the seed for each iteration. Another part in our insights is to amplify the degrees of IC between different libraries. To achieve that, mutation rules, which had frequently generated models that amplify the IC degrees, should be selected with a higher probability for further mutations. Given a seed model S and its mutant M, Lemon will get their outputs on all libraries. By using the metric mentioned before, we can get the IC between different library pairs for each of them. Lemon will calculate the cumulative IC for M and S respectively, that is, the sum of the IC values for all library pairs, called ACCM and ACCS. If ACCM is greater than ACCS, it means that the mutant of the seed model has enlarged the IC. Then, the mutation rules selection history would be updated at the end of each iteration. In the selection strategy, we define a priority score ratio MU to indicate the possibility of MU being selected. Ratio MU means the number of times a model generated by MU amplifies IC degrees over the total number of times MU is selected from mutations. We use metropolis hasting to determine the rule chosen in each iteration, in which mutation rule to be selected depends on the most recent behavior of each mutation rule. More details about MH could be seen in our paper. Here, we use an example to illustrate the effectiveness of lemon. An initial model correctly predicts the image as code, both on TensorFlow and Theano, and the IC value was 0.128. When we use a mutated model, the output of TensorFlow is code, but the output of Theano is uncoded, and the IC value was 0.734. Therefore, the mutated model generated by lemon can detect the bug that the initial model cannot detect. In our study, we evaluate lemon on 12 models, 6 datasets including image and sequential data, 20 released versions of the 4 libraries in total. In RQ1, we first investigate the effectiveness of lemon in terms of new bugs detected in the latest release versions of libraries, whose results are shown in Table 3. In total, lemon detects 24 new bugs in the latest release versions of these libraries, including 13 bugs by analyzing the detected ICs, 6 crash bugs, 4 NN bugs, and 1 performance bug. 7 bugs have been confirmed and 1 bug has been fixed. For example, as for the Keras performance bug, a user said Keras may leak memory when loading a model in a loop. As for another bug happens in TensorFlow batch normalization layer, a user said she or he met the same issue and thought there is a bug in TensorFlow. Lemon finds 1 bug in the transpose operator in MXNet. The buggy transpose operator only relies on the input tensor for shift inference, causing to throw the exception message about dimension checking, even if the model is valid. The fixed transpose operator uses both the input tensor and output tensor, and thus is able to infer all unknown dimension sizes based on these tensors, and the user confirmed the bug. Besides, one major contribution of lemon is generating mutated models, and thus it's interesting to investigate the unique bugs detected by mutated models. In detail, we investigate the effectiveness of lemon and the unique bugs of the mutated models for each experiment of differential testing, each used model, and each studied library, respectively. As shown in the red box, for the initial model MXNet, L represents the bugs that the lemon can detect, and M represents the bug that the mutated model can detect, but the initial model cannot. I represents the bug that the initial model can detect, but the mutated model cannot. It can be seen that the mutated model can detect bugs that the initial model cannot, and all the bugs initial model detects can be found by mutated model. The conclusion is consistent across all used models. We further evaluate whether the mutated models can amplify the IC degrees compared with the initial models, which is our contribution to solve the second challenge. Vm and Vi present the average IC degrees achieved by the mutated models and the initial models across all models. It could be seen that the mutated model generated by Lemon could improve IC degrees with a rate range from 27% to 357%. As mentioned before, we use heuristic-based strategy to generate models to amplify the IC degrees. So how is the effectiveness of it? We answer this question in RQ2. We compare Lemon with its variant Lemon R, which uses a random model generation method. We choose versions of 4 libraries in experiment E2. For Lemon and Lemon R, we generate mutants for each initial model in 1 hour. In Table 6, columns 2 to 3 present the total number of IC only detected by the mutated models generated by Lemon or Lemon R across all the models. Columns 4 to 5 present the total number of IC only detected by the initial models. Columns 6 to 7 present the average improved rates of IC degrees achieved by the mutated models over initial models. We can see that Lemon detects more unique ICs than Lemon R, which are missed by the initial models. And the average improved rate of IC degrees achieved by Lemon is always larger than that of Lemon R for each library pair, which demonstrates the effectiveness of heuristic-based model generation. We have released our tool on GitHub, and more details on Lemon can be found on our homepage if you are interested. In this presentation, we first introduce our original problem about deep learning libraries testing, and then, in order to solve the 2 major challenges, we propose a deep learning library testing approach based on model generation. We conduct 5 experiments on 12 models and 6 datasets, and the results indicate the effectiveness of Lemon in detecting bugs in DL libraries. And thank you for your attention.